Hello everybody and welcome to another day of CS 302. Today is a special day for the class because we have 2 weeks left of the semester and we got a lot of material to cover. And so on Thursday is Thanksgiving. So technically speaking, we have class on Wednesday. But what I'm planning on doing is I'm going to have a longer lecture today to cover some of the material that I wanted to cover on Wednesday. And that way, I can give you to watch as assignment, homework assignment, the minimum spanning tree lecture from last semester so that you can get going on the assignment. What that means is we'll probably end up having extra time on study week, but that's okay because we can use it to review for the final. So that's the plan. So this lecture might go a little bit extra, and that way we can cover both the material from Monday and Wednesday, and then you will have to watch a lecture as an assignment as well. Okay, so there we'll see. We're gonna have more time rather than less. Okay, because I really rather have less things to do in study week and just get you going on that next assignment. So yes, that's the plan. Okay, so no time to waste. Let us go ahead and begin. Oh snap! Hold on. I didn't link the iPad to the monitor, so it's not going to stream. Give me 1 second. Okay, here we go. All right. There we go. Okay, so last time we introduced graphs and we covered a lot of terminology and some definitions and that kind of thing about graphs and some concepts and basic things. Today, what we're focusing on first is about how to represent a graph in a computer. And we need to do that because that is what you got to do for the assignment is you got to store a graph in your computer. So we need to know how to do that. From there, we are going to go ahead and talk about breadth first search and depth first search. So I'm actually going to go ahead and add those into these. Whoa. So after we learn how to store something in the computer, so think back to how we covered trees. We first basically covered visually what it was, and then we covered how to traverse it, which in this case is depth first search and breadth first search, and then we also cover how to store it in the computer, right? Those were the James Bond assignments and that kind of thing. So in this case, we're kind of switching the order a little bit. We are first covering how to store it and how to traverse it. And that's because I want to, when I go over depth first search and breadth first search, I'm going in a more sort of technical view because it's kind of useless to go in an overview, like just a generic. I mean, we'll do that too, but you don't really understand how it works unless you see it more from like a coding point of view. Okay, so that's, as you can see, that's quite a bit to cover. So we shall go ahead and begin. So again, computers, zeros and ones. So just like trees, we kind of have two choices when it comes to actually storing the graphs in a computer. And that is, we can either use pointers. So how we store like actual trees, most of the trees except for heaps. Or we can also use some sort of array, which is how we had heaps, right? So if you think about trees, this is how heaps were, and this is how like AVLs were, okay? So ultimately, most of the time, you'll find that I would say the majority of the time things are stored in an array for the graphs. However, the same problem that happens when you deal with linked list versus arrays happens with graphs. If it's a graph that's ever changing, like you're going to insert nodes into a graph or remove them, then you have to go with the pointer approach because the array version is like fixed size and you cannot you can't basically like add things or remove things because you have to resize the entire array. Okay, so the two ways that you can represent a graph is with an adjacency matrix and an adjacency list. The adjacency list is more of like the pointer sort of version, and the adjacency matrix is more of the array version, and in this case it's a 2D array, not a 1D array. But technically speaking, both of those can be represented as text. So what I'm going to do now is I'm going to take a graph that I have here prepared ahead of time to save some time, and I'm going to show you how you would store each of them. How would you represent the graph as an adjacency list and as an adjacency matrix, okay? So let me go ahead and copy it. So first, here is a graph, and this is a rather simple graph. And we have to do this twice, actually, because I want to show you how to store a directed graph and also a undirected graph, okay? It's very similar, but there's some differences that are important to understand, okay? So first of all, mathematically, if I was to represent this graph, you know, with the formula that I showed before, with like G is an identity of B and F. So looking at, wow, we did so much stuff. Okay, this stuff. So remember that we can use edges. We can say V to W or W to V, in which case these are the same because it's undirected, versus parentheses where it's directed, and we're saying that V is going to W. So in this case, if we can use that notation to represent any graph. So if we have the following graph that has 4 vertices, and there are certain edges going from A to B, A to C, B to C, and B to D, but these are undirected, so they're going in both directions, we can represent this with the following. Okay, so what I'm looking at here is I have the graph G is an identity of B and E, in which case V is all the vertices. So we have A, B, C, and D, as you can see here. And we have the following edges. We have edges going from, why did I use parentheses on that one? I should not have used parentheses. I should have used curly braces on those. My apologies on that. We gotta change all of these to curly braces. Oh, I see what I was doing probably. I was trying to, what I was trying to do is show you that it would be a combination of all of this potentially. So this could be an actual representation of this, but we have to include both directions. Alternatively, you could also do this by doing the following. The whole reason I did that ahead was to avoid having to do a billion curly braces. So we got A to B, and then we got, let's say, and it doesn't matter which order you put them on in this case. So we could say B to C, or we could say C to B. There's no difference. Then we could have, let's just put D to B in this order so you can see that it doesn't matter. It's not alphabetical. And then we need one more, or which one are you missing? A to C. Yeah, A to C we're missing. Okay, so we got 4 edges, 4 lines. Yes, okay. So both of these would work. This one or this one. However, this is to be more pure, like pure, more traditional would be like to use this method because it's an undirected graph. And so this is more of like a combination of a directed graph. So, you know, we could put that one aside for now. Okay. So this is going to be the math representation of this graph right there. If I give you this right here, just this part, then you should be able to draw that graph. Okay. You should be able to do that. And it may not look the same, you know, if you do this, just looking at this. And of course you got to put some weights associated to this thing. So you know, we can say A to B is 1, and then B to C is 5, and then D to B is 2. Or sorry, no, this is 1, and then this A to C is 2, right? And so if you want to include those values within here, you could put them as a comma, or you could put them somewhere in here, so you can put the weights. But the point is that let us go ahead and say that we are doing like an unweighted version for now. Okay, so let's maybe let's just get rid of the weights for now. Okay, let's just think about the graph without weights to go like extra simple. Okay, so looking at this, I can redraw that graph because I can go ahead and say, okay, I'm gonna have an A, a B, maybe like put some space here, maybe like a C, a D, and an E. Okay, oh, there's no E, my bad. So I only have four vertices, okay? And so I can just draw the lines. AB, so AV, okay, BC, BC, DV, DV, and then AC. So there we go. So now you might be looking at, well, those don't look the same. They may not look the same, but they are the same because they have the same number of edges and the same number of vertices, and those edges are the same ones, like this, going from each to each. In fact, what you're looking at now is like, we would have to kind of flip it like kind of like that, so it would look like the one above, right? So I can try to kind of manipulate it. So basically we can rotate it like this and then just mirror it, which I don't know how to do. I know there's a way to do it on the iPad, but whenever I actually do it, it's because I don't want to do it. And then when I want to do it, I don't know. But there is a way to mirror the image on the iPad. I just don't know how. Yeah, I don't know how to do that. My apologies, but you can do it. So anyways, you can, hopefully you see that if you look at this in the mirror, then it would basically convert into this, which is essentially the same thing we have up there. See that? Okay, so this is the same graph. It just looks different, but it's the same, okay? And that means that the math is good. So what we want to do is we want to convert that into something that we can store in the computer. So what we do with the adjacency matrix version of this is we are going to do a 2D array, and the size of the array is going to be the size of the number of vertices that we have. So in this case, we have 4 vertices, so we are essentially going to write a 4x4 array. And again, to save time, I went ahead and kind of did it over here. Okay, so here I have, and let's just go ahead and erase the numbers for now. So here I have a 2D array, okay? And that 2D array is just indices, but I am going to define a certain index to represent a certain vertex, okay? Now, mathematically, I have chosen that I'm calling these vertices A, B, C, and D. But when I'm representing it in the computer, I can just make them be indices, so 0, 1, 2, 3, right? It doesn't matter the order that I store them in as long as I can identify them, right? And you know, you can use object-oriented programming, and instead of making these be actual like car array, you can make it be an array of entities, and those entities could be vertices, and then each of those could have a special member variable string that's called like ID, and then you can put the A, you know, B, C, D, or whatever, right? So that is just like you know, basic things that you can do to label these things in the array. So the array is actually the data that you're storing versus just like a car array, okay? But you could also store it as a car array too. It doesn't matter as long as you have some sort of key. In fact, you could use like an enum too to implement this. There's so many ways you could implement this, but the point is that you need a 2D array that you can basically label each of these vertices with a certain index, in which case we're doing A, B, C, and D for 0, 1, 2, and 3, okay? So the first thing that you should understand about this is that one of the dimensions you can think of as the from, and the other one the to. It doesn't matter how you do it. I have chosen arbitrarily to choose the vertical one to be the from, and then the horizontal one to be the to. And what I'm saying is, I'm going to go ahead and put a 1 wherever there is a link. And then I'm going to put a 0 wherever there is no link. And by link, I'm talking about an edge, okay? So what that means is that if we look at, for example, the connections coming from A, we can see that A is going to both B and C, but not D, right? So if A is going to B and C, but not D, we can say on the first row, the one red that says from, you know, A is going to A. We're going to say that, sure, A can go to A because you can go to yourself, no problem. It can also go, come on, to B and C. So we're going to put a 1 for B and a 1 for C. However, it cannot go to D, and we're talking about directly, like I'm talking about if there's a path. I'm talking about if you can go straight jump kind of thing. And as you can see here, there is no line from A to D. Therefore, I'm going to go ahead and put a 0, okay? So that's how you would do it looking at the picture. Now, looking at the math, so looking at that, we can also achieve the same thing. If we, all we got to do is basically see which of those little pairs contains the letter A in it. And if it does, then we can just add whatever the other letter is. So for example, if we look at B, we can see that B is contained here. It's also contained here and also contained here, which means that A, C, and D are all connected or adjacent to B. So we can go ahead and mark that out. So we have A is connected to B, we have C is connected to D, or sorry, to B, and then D is connected to B, right? And then B is connected to itself because that's always the case. We can of course change that, but I'm just saying usually for the most of the algorithms you do, we consider that to be something that we just add. So because of the way that this is done, this is why I have that red line, you can pretty much just automatically fill out the diagonal, because it's kind of like what's that? I think there's that one game where it works like that, where you just fill the diagonals because those are always empty. I don't know, maybe I'm thinking of something else. But anyways, I hope that makes sense. That we just fill all the diagonals because those are always the from and the to are the exact same. Okay, so we're gonna say that yes, you can go from yourself to yourself. All right, so let's go C. So C, we can see is connected to B here, and it's also connected to A, right? So we go ahead and fill B and A for C, so B and A. And we don't see anything for D, so we put a 0. So now I have shown you how you can get it from both the math and from the picture, right? Finally for D, D is only connected to B, as you can see, because there's only one line here. That can also be seen to be parent because you only see it show up once here. Okay, so let's go ahead and fill that out. All right, so what you're looking at here is an adjacency matrix. And the word adjacency being because it means things are connected, right? We talked about that term last time. As you can see, the diagonal is ones, and also, can you notice something about this adjacency matrix? Like, does something appeal to you about the way the numbers are ordered in the thing? Like, do you see something interesting here? For the sake of time, I am going to go ahead and tell you. Mirrored, yes, there you go. I'm happy. Well done, well done. So yes, this is indeed mirror. So this is a mirror, and by that I'm saying that this and this are mirrored, mirror with this too. This one is mirrored with this one. This one's mirrored with that one. This one's mirrored with that one, and of course the diagonal doesn't have it. It mirrors with itself, I suppose. So yes, this is indeed a mirror. This is what happens when the graph is undirected, okay, or unordered. And why do you think that's the case? Because things go in both directions, right? When you have an edge, it goes in both directions. So therefore, it shows up on both sides. It turns out that any time that you're working with an undirected graph, the adjacency matrix is going to basically be a mirror of it, whether it's weighted or not. So ultimately, from an implementation point of view, if you're actually storing this in the computer, you could save some time by only storing half of it, and you could regenerate the other half automatically that way. So this is both a good thing and a bad thing. Because bad because it's inefficient if you don't do it. Good because you don't have to do it, I suppose, if you're smart about it, right? So yes. Finally, I don't think we talked about weights last time, or did we? No, we didn't quite talk about weights yet. So that's okay. We're gonna revisit this example in a minute with a weighted graph, but right now we're gonna keep things unweighted. Okay. So now what I'm gonna do is I want to move on to talk about adjacency list, and then come back and talk about the weighted version of these graphs. Okay. So for now, this is all you basically do. And by the way, when you're looking at an adjacency list in the real world or whatever, or adjacency matrix, sorry, you may not see zeros in it. You might just see like empty blanks. That just means there's no edge. But in the computer, you can't just say empty. So we like to use the word 0 and 1 to represent connection and no connection. Okay. But again, you could use any numbers. You could use 5 and 6 for all I care, right? Also, I want to point something out. Suppose that we have a graph with 20 vertices, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we got a big graph, right? And then maybe we got, a couple of edges in here. That's it. Okay? That looks like a constellation almost. But yeah. So here's the thing. How big is this graph going to be? Let's say you're storing it in an adjacency matrix. Well, if it has 20 vertices, it's going to be a 20 by 20, right? So it turns out that the majority of it is going to be zeros, and very few things are going to be ones. So for the first time in the semester, I think, second time, because we did talk about with hashing, we're going to be more interested in the space complexity rather than the time complexity. So it turns out that when we're talking about storing something, like it is here in this case a graph, it's more irrelevant to talk about space, but time too. With time, this is great because it's an array. So like I can, as long as I know from where to where, if I want to see from 2 to 3, which is from C to D, I can just type that in here and then I get it immediately. It's O of 1. It's constant time to be able to get whether an edge exists or not. This is cool. This is great. That's Adjacency Matrix's greatest power, is that you can immediately find out whether an edge exists by going there, right? You can imagine that if we had this stored as pointers, the only way to find out if an edge exists is to traverse this thing and go there and then see if the edge is there or not. Well, here's the catch. While this is a great thing, when you're storing something like this in a adjacency matrix, it's very wasteful of space because it has a bunch of zeros everywhere, with the exception of what would be 1, 2, 3, 4, 5, 6, 7, 8 lines. So 8 ones plus the diagonals, which would be 20 of them, right? So in something that has a spot for 400 things, 20 times 20, you're storing essentially, what did I say? Something like 27. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 29 things because of diagonals, right? So how full is this? Well, it's less than 10%, I'll tell you that. In fact, it's like maybe 7%. That's very inefficient in terms of space complexity. Okay, this kind of goes back to when you were thinking about like hash tables and versus like arrays versus linked lists. So it's not so great for graphs that are what is considered to be sparse. So let's talk about those two terms actually. That was a good time for that. Let's just get rid of this. There's a term called sparse graph and a term called dense graph. These are very subjective terms, but it turns out that a dense graph is considered a graph that has a lot of edges in it in relation to the number of vertices. Okay, so a dense graph would be one where everything is connected. In fact, a strongly connected graph is more than likely going to be a dense graph. A sparse graph, on the other hand, is a graph that has a low amount of edges in comparison to the number of vertices that it has. This would be an example of a sparse graph because we have, of all the edges we could have, which is practically 400 edges almost, minus, we're not counting the 20 that you're going around, so 380. Of the 380 edges we could potentially have in this graph, we only have 29. Again, we're counting the same ones. We only have 9. 2, 4, 6, well, it's 8. Where did I get 9 from? 2, 4, 6, 8. I don't know where I got the 9 from. There's only 8 lines there, but, or here, we'll just leave it at 9 and we'll just, bam, 9. Okay, so that's a very, very, very low number of edges. So that would be considered a sparse graph. It turns out that an adjacency matrix is very fast, but it's typically better to use with a dense graph because otherwise you're being wasteful of space. Okay? Because remember, when you're dealing with an array, you have to declare the space to store all of these edges potentially in it. Edges that don't exist, that it's just wasteful in that sense. Now, could you go fancy and do like some sort of like what they call what is it called? That arrays that are not square, but like you do nasty memory allocation. Oh, what are they called? Shoot, I forgot. Sparse arrays? No, that's not it. There's a term in the. I'll try to see if I can Google it later and then post it on the description. But there's a term that you use for arrays that you don't just define to be like square, but you're like cheap on space, so you just like define it based on how much space you need. So like it could turn out that your array would look something like this. Instead of being a square, it might be like that. So you're only defining the space that you're actually using. Okay, that has a name. I don't remember what it's called. I learned it a long time ago. It's just a name to basically explain that, okay? But unless you're doing something like that, which again defeats the purpose, because then if you want to add an edge, then you're screwed because you have to like redeclare the whole thing. So that is a disadvantage. Yes, I think it's ragged, not jagged, but I think ragged arrays. So I think that's it. Thank you. At least I think I've heard, I mean, it might be jagged, but I've heard of the word rag before. By the way, your name is like dark, so it didn't like show up there. That's cool. But yes, so I think it's actually ragged, but maybe you're right. Maybe it's jagged, but it rings a bell now. You said ragged or jagged. Okay, so it's one of those terms. So yes, and that's what you call that. So that's something that like you learn at some point. So is it jagged? Okay, so I wonder where, maybe just it's just blurry in my head. But yes, okay, so jagged array, that is. So it has a special name, and it's just one of those things that they make you code at some point in life, just to show that it's good. Ragged is equal to jagged. I don't know. But anyways, I'm glad you guys found that out. So I will remember that. I'm going to type it here, and then I will read about it later. Ragged, jagged array. In computer science, a ragged array, also known as a jagged array. Oh, okay, so it's both. Okay, so I don't feel so bad that I remember the word ragged then. Well, I didn't remember either, but at least it rang a bell when you said jagged, actually. So that's cool. I suppose my memory was not a adjacency matrix or a dense graph, but rather it was a sparse graph, my brain, right? The neurons in my link were sparse in that area. Okay, so anyways, there isn't a defined percentage that I've been able to find in like the years that because this always comes up like, okay, so how many edges would be considered a sparse graph? Like, is there some sort of threshold, like 20%, 30%, or whatnot? I have not been able to successfully find like an answer to that from my search among the internet. So what I've given people in the past as a answer to that is, I think, hold on, I have it here. I think it's like, I think I said more than 20% would be considered dense, I think. Hold on, no. Let's see. I don't know what that would be. Who knows? I'm looking at the notes of like last semester, but it's just like all over the place. Because I mean, it makes sense when you're drawing it, but then you erase things, it just goes. So I will leave that as an exercise for you to figure out. But essentially, I would, you know, for sure, I would say maybe less than 50%. I mean, more than 50%. I would say for sure more than 50% would be considered dense. I would also say for sure maybe less than 10% would be sparse. But anything else like would be considered like a gray line or gray, gray boundary. Okay, so that is why for the definition here, I'm gonna say a low edge to vertex ratio, and here I'm gonna say high edge to vertex, or I should say vertices or vertex, I don't know, ratio, okay? Because there's no real define. I mean, you go read a book, I'm sure they will have a number, but then you go read a different book and they have a different number. So, it's a nice term to use, and it turns out that adjacency matrices are better for dense graphs, and the other method that I'm going to show you, adjacency list, is better for sparse graph. But again, nobody tells you what a sparse graph really is. So we'll leave it at that. You can figure out on your own what is ideal, okay? No defined exact number. It's kind of like when you're talking about hashing and load rate, like the load factor, there isn't a specific load factor that guarantees you should rebalance. But the higher you go, the closer you get to like the max, you're gonna have more collisions. It's kind of like that. It's subjective to what you're doing. Okay, so again, I haven't talked about weights, but I think that's all I'll say about adjacency matrix. Okay, so now you can see that in the computer, when you're working with a graph, you can store it like this, and then you can figure out if there's a connection between things. I haven't shown you what to do with a graph yet, like traversals or Dijkstra or minimum spanning trees. So you don't really know what to do with a graph now you have one, but at least you know how to store it in the computer. This is nice because, again, there's no pointers involved. This is like the equivalent of heaps, okay? Like how you store heaps in arrays. This is kind of like that. Okay, moving on, let us go ahead and represent the same graph using an adjacency list, okay? Which is typically stored in a computer as as a linked list. Pointers, you know what I mean, okay? So for that one, do I have a pre-done ahead of time somewhere? I do. Yes, I do. Perfect. Okay. But actually, I think instead of copying it immediately, I should draw it for you, because otherwise you might get confused. Okay. So this is the other method of not just storing it, but if you're reading from a file, like let's say I'm giving you input. If I'm giving you input, I could give you a little matrix like this, you know, just space it out, you know, give you the dimensions ahead of time, or make you figure that out on your own. With the adjacency list, it's kind of like that too. You'll see some input text like that. Okay, so adjacency list is kind of like a what would be a good example? Kind of like a friend list. If you're looking at like a friend directory. Okay, so what you're gonna do is you're gonna have a little line there, at least when you're representing, at least with a drawing, and then you have all your vertices A, B, C, and D. And all you list on the other side is what it's connected to. So for example, A is connected to both B and C. Okay? As you can see here from here, we got A and A, right? So what you do is you just put B and C there, separated by a comma. Okay? I don't know where this thing came from here. Same with B. B is connected to three things. It's connected to A, it's connected to C, and it's connected to D. So you can just go ahead and write A, C, D. Now you don't have to put them alphabetical. I'm just doing that by default, but like here, let's do that for C. Let's put B and A for C, because C is connected to both A and B. Okay, so yeah. And finally, D is connected just to B. So this is essentially an adjacency list. Now you might be like, oh, this is so much nicer than this. Well, yes and no, because I mean, if you're reading this from an input file, you might see things like this. You might see like a character, and then the other characters like this, and then B could be like A, C, D, C, B, A, and then D, B, and then you could use like get line to get each of these lines, and then the first one you know is the from, and then the rest is the to, you know, so you can read. It's nicer to read them from a file if you're reading in an adjacency list. There's no denying for that. But problem with storing in the computer like this is that you cannot immediately find out if there's an edge or not. Because if I tell you, answer me this, is there an edge from B to C? What you need to do to figure that out is first, you need to go to B. Yes, you can do that immediately. You can go to any of these immediately. So like, again, this is 0, 1, 2, or whatever. That you can go immediately at, no problem, constant time. However, think back to kind of like hashing with close addressing, which this is kind of like that. In fact, you could actually store this in a hash table with close addressing like that too. But if you have collisions, the whole thing breaks, so don't do that. But the point is now here, just like with hashing with seek time, you know, when you had a collision with close addressing, you had to search through the linked list, right? So the thing is, here is the same thing. If you want to find out if there's an edge from B to C, you have to search in the red square those three things to see if C is in there. Of course, you can see it immediately, right? Okay, sure. Imagine that this is a graph of the entire city of city of LA, and like a map. This is like all the streets in there. There's going to be a lot of things linked there. Okay, for some places at least. That means you have to search for that. Linear search. Linear search is not good, right? Linear search is like end time. So that is a slow thing. It's not constant time anymore. That's the disadvantage of this. Advantage though, look at that. I'm not storing any irrelevant information, especially here that it's a undirected graph. I am storing only what I need, which is the name of the from and then the name of the to. There's no repeats, which is why this is great for reading in from a file, because you keep the file size smaller. Disadvantage, of course, seek time is not good. Okay, so if we go ahead and we look at the space complexity with numbers, it turns out that the space complexity of, I actually have them up here, of the adjacency matrix and the adjacency list is going to be O of B plus E. That's the number of vertices and the number of edges, okay? However, this works for an adjacency list. However, with an adjacency matrix, it's actually B squared because you have that, right? Here with the edges, you can see that if we were to have, if this was a not just a strongly connected graph, but like a graph that had every single possible edge. So like if we have a graph like this, every possible edge would mean that, right? Everything has a degree of 3 coming out of that. So this would mean, if you count the number of edges here, we have 1, 2, 3, 4, 5, 6, right? So we got 6 of those, and then we got 4 vertices, right? So 4 plus 6 is 10. If we have 4 squared, that is 16. What did I do here wrong? 1, 2, 3, 4, 5, 6. 1, 2, 10. Why is this not adding up the way it should? Okay. Ignore that. It turns out that if you have a graph that is like that, it's going to be practically the same as if you were doing the adjacency matrix version, minus the going to the same. All vertices of degree 4. Well, it's degree 4 if you consider going to yourself, but here they're not going to them. So I don't know what I did wrong there, but it should add up. Maybe I'm thinking something wrong. But yeah, so adjacency list is great for space, but if you have a graph that everything is connected, like very high degree graph, very dense graph, then you lose any advantage to it because it's still going to take the same amount of space to store it. I'm trying to figure out as to the why that didn't work. I mean, but if I count these things, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's just do an adjacency list where everything is connected between like 3 things. Let's just do 3 things, okay? So what that would look like is like this. We have BC, AC, and then BA, okay? So we're storing 1, 2, 3, 4, 5, 6, 7, 8, 9. So this worked on this, but I don't know what, I must have messed something up. As you can see here, we're storing 9 numbers, right? 9 numbers is the same thing as 3 squared. It just turns out that here we're saying 3 plus 6. So I don't know what I must have messed up something when I was doing that drawing, but this should, what I'm trying to show you is that if an adjacency list is storing a graph that's very dense, that the space savings is lost in comparison to the adjacency matrix. But the thing with the adjacency matrix is that you have that O of 1 seek time, which you don't with this. So you only want to use an adjacency list as a storing method in your computer if you have a sparse graph. Otherwise, you lose all the benefits and you still keep all of the disadvantages. Make sense? So yeah. I don't know why the version didn't work. I was trying to see. Maybe because I'm not considering the from. 3, 6, 9, 12. Yeah. I don't know. Because if I have the 4-way version, which is basically A, B, C, D. This is B, C, D, C, D, A, D, A, B, and then A, B, C. So as you can see here, that is basically 12 plus 4. So maybe I was doing math wrong earlier, but you can see that's equal to 16, which is the same thing as 4 squared. Okay, so I don't know. Whatever I did earlier was screwed up at some point. But yeah, so the space complexity of this thing is always going to be the worst case, which is V squared. And this one is going to be B plus E, which may end up going to this when it becomes a dense graph. It just becomes closer to that, okay? And finally, if you're storing this as flat out pointers, then you're just storing them as pointers, right? But the point is that you can generate those very quickly from the adjacency list. So if that's what you're doing, then that's a better way of reading it. If you're reading from adjacency matrix, You can still make the graph with pointers, but at that point you might as well just keep it as an adjacency matrix. Unless you know that you're going to be adding or removing nodes to it, in which case I suppose it's okay to leave it as a adjacency list. Okay, so before moving on any further, let us talk about weighted graphs. Okay, so weighted graphs are graphs where, oh, actually, let me point something out here. One more thing about this, okay? Adjacency lists are ideal for directed graphs because for undirected graphs, there isn't really an easy way to like save space. It's still better for sparse graph overall, but I'm just saying if all things are equal between both methods, adjacency lists, there's no way to, like, okay, if it's an undirected graph, you can see how it is redundant for me to have this here because it's already being represented in the line above. But there's no real easy way of achieving that. So that causes a bit of an issue with this. So like if I wanted to really be cheap about space here, then I should be able to basically get rid of this here because it's already covered in this one. And then this one here too. And this one here too, right? So technically speaking, if I know it's an undirected graph, that right there on the left is enough to draw the graph that I had there, right? Because I have 4 edges, 4 numbers, or 4 characters there, right? However, you don't really see that when you're looking at an adjacency list. Like you don't see that version of it. You see this whole version of it. So it just kind of makes it automatically a directed graph. So there's, you know, whereas with the adjacency matrix, you know, given some input, it's very easy for you to just get a ragged array, as we said, and then you can just generate that ragged array or generate the mirror version. So that's an easy way to save space. This one, you don't really see that other version shown, okay? So, yeah, just FYI that if you see an undirected graph that shows like that, then you don't have to do those extra edges. They don't, but, you know, it's weird if you don't, okay? Any questions so far about adjacency lists or adjacency matrices? Okay, so now before we go further, I would like to talk about weighted graphs. So the idea of a weighted graph, and I think I might have mentioned it last time, but you know, better to refresh, is if we have the following graph. We are saying that there exists a path, here let's label these as A, B, C, and D. I'm saying there exists a path from A to D, right? In fact, there exists 2 paths to get there. You can go A, B, C, A, B, D, or A, C, D, right? However, I am not discriminating between them in terms of which one's better or faster. But that is not always the case when we think about networks, right? If we are saying that this here is LA, and then this here is like San Francisco, and then this here is like I don't know, San Diego, whatever the San Diego region is, and then here's Vegas, and this is an internet connection. You know, it might take longer to go to San Francisco for the signal and then to Vegas than to go to San Diego. Or maybe to make this a little more blatant, let's make this be like Victorville or something. Okay? In this case, this signal might take maybe like 1 second here and then maybe like 2 seconds here, okay? That's not the scale. It's probably more like 25 milliseconds, if anything. But yeah, okay? Just go with me with this. On the other hand, to San Francisco, this might take like 2 seconds, and then it might take 2 other seconds to go there. Actually, that would also not be to scale at all. So this would be more like 4 seconds, okay? Going to the desert or something. So what this means is that if I'm trying to send a signal, I would rather send it on this route than on this route. Because the route above is going to give me a total of 6 seconds, and the route on the bottom is going to give me a total of 3 seconds, right? So weighted graphs, which is what you call these values, we call them weights, means that the edges have an associated weight to them. And that weight represents a lot of things, but can be time, distance, or any other quantifiable measurement to communicate information, people, or anything between two vertices or nodes. Okay? So we would like to represent that in our computers when we are coding in an adjacency matrix, an adjacency list, or just pointers, right? With pointers, we can just add a class variable and keep it, you know, it's like putting in a linked list, like a weight value next to the next pointer or something, right? But when it comes to an adjacency matrix, that's actually very, very convenient, because all you need to do is, instead of putting zeros and ones, you can just put in the weights associated to those edges. And then if there is no edge, you gotta be a little careful here. If you put a 0 there, you might be time traveling at this point, because you might say that, or teleporting actually. You might say that you're teleporting from like San Francisco to Vegas or something, because you're saying it takes you instant time. If you put negative time, then you're going back in time when you're going somewhere, which is even worse. So what you need to do is you typically want to say something like infinity, so that the edges that don't exist take infinity time to get there. And that's how we can mathematically get around that weird scenario of no edge for a weighted graph. Okay? So in a computer, what you can do is you can just go ahead and do something that before it overflows. So like 2.1 billion is your infinity, basically. Okay? So going back to the first example that we did today, now let's go back and add some weights in there. So I'm going to go ahead and just add the weights that I had before so that I can copy what the graph looks like to save time. Okay? So if we have the following weights, then actually I can just draw it down here. This is what it would end up looking like. Hold on. Move this here, and then we move this here to make it big. Okay. So what I'm doing now is I decided to pick A to B to take weight of 1, and we're doing undirected graph right now, but this will also work for directed. And then we're doing 2, 5, and 1 for the other weights. As you can see here, I decided to arbitrarily choose -1 to represent infinity, because I said that you can't travel in time. But this is another thing that you learn in the analysis of algorithms. There are algorithms that can handle negative weights when it comes to things like shortest path or things like that, like distance measurements. Not all algorithms will, though. But typically, we don't see negative edges being used in graphs because, again, that kind of represents like time traveling, and it really screws things up. So I chose to do -1 and just hard code that in my code implementation of this as a sign that there exists no edge. However, if you're dealing with a graph that does have negative edges and they're allowed in whatever code you're doing, I mean, you could be doing time traveling for all I know, then you can't choose that to be your infinity mark. For that, you again can go with what I said. Pick a really, really big number before it overflows. You can use, in the computer, there is a shortcut. It's called int max. I think it's like int underscore max, and that'll give you the biggest integer that your C++ compiler can handle, and it'll just fill it in with that. So you can do like a define called infinity int max. I think, let me really fast Google. Define int max in C++. Oh, there's also a min apparently. So there's a Geeks for Geeks links, which I'll post in the description. And so based on this, yeah, so it is int max. So that'll give you the numbers. With a regular integer, you know, these are the numbers before it basically overflows. And so what you would want to do is you would do something like lowercase, define INF and then int max. I don't think you need a semicolon after a define. I can't remember for right now. I haven't done that in a while. And then you could do like the same for like -infinity and inf and so on. And what I'll do is that'll make sure that that number is the biggest it can be. so that it doesn't screw up with your algorithm if you have negative edges. But if you don't have negative edges, then just pick a number arbitrarily, a negative number ideally, and then just hard code that to be your infinity mark. Like if this edge is equal to -1, then we consider that to be infinity, which means there is no edge. Okay, so anyways, let's see what happened here. So we got from A going to B, as you can see that it's still to 1, but now A going to C is a 2 because that is the value of the weight. There is nothing going from A to D, so we put a -1. Looking at B, we can see that it goes to C with a value of 5, which is why that weight is there, 5. And we can see that it also goes to both A and D, but it goes with a weight of 1. And of course, you still go to yourself. So here's the thing. If you're going to yourself, that's nothing you gotta play around with. You may choose to say that it takes instant time to go to yourself, which would make sense because you're already there. So that would be a good usage of a 0. So you might see an adjacency matrix where the diagonal is a 0s. That means that they're saying it's instant time. So this is why you gotta be careful if you're dealing with a weighted or unweighted graph, because you can see some of these sort of standard things like 0 being no weight, no edge, change depending on what you're looking at. Okay. So this is more of what you will be looking at in your assignment 11. Okay, so is there any questions about a weighted graph? And if you, again, this is mirrored, by the way, because it's undirected, but let's go ahead and very quickly do a directed version of this graph. And in the meantime, please come up with questions if you have any about adjacency matrices. Let's just say that maybe we have this going like that, and then we have that going like that, and then we have that going like that, and that going like that, and then we have that going like that, okay? So in that case, this is gonna completely change. So I'm just gonna erase these so I don't screw up. And just while I'll look at the chat in a minute while you guys figure that out if you have any questions. So A is going to B and C, so that is a 1 and a 2. B is going to D, so that's a 1. And then C is going only to B with a value of 5. D is only going to be with a value of, let's just say 8. Okay, and then the other ones we are gonna just say are infinity. Infinity and beyond. If a weighted directed graph has A to B of weight 3, can B to A be of different weight? Yes, it can, just like I just showed there with D and B. So that's the beauty about weighted graphs, that you can have. It's like think about this. Suppose that you're driving from LA to Vegas and you're on the 15 and there's road work happening in one direction. So it is possible that it could take you 2 hours to go to, well, not unless you're speeding. It takes you 3 hours to go from Vegas to LA in one direction, but then on the other direction from LA to Vegas, it takes you 5 hours because there was a car crash or there's a construction going on, or you got pulled over, I don't know. So essentially, yes, you can have things going in like this with different weights. There's a significant scenario where that can happen. One network might be more congested than the other one. So that's a good question. I like that. Okay. All right. So, oh, that's sad. I had it here actually from last semester. Oh, that's interesting. Okay, let me copy that. This is actually pretty smart. I forgot I thought about this. I had this defined from last semester to make infinity. That's hex version for the biggest number you could have. So, yeah, that could work too. Oh, that's sad. I wish I had remembered that. But now I do. I also sometimes use the infinity symbol. If you watch the lectures from last semester, I was using that infinity symbol instead of writing the word INF as well. But, oh, here's the sparse and dense thing. So I said last semester that sparse graph was for sure anything less than 30%. A dense graph was for sure more than 50%. And then the 40 to 50% range was the gray line. So, yeah. As you can see, those are not things that are very clearly defined. Okay, so anyways, moving on to adjacency list, let's talk about how to do that one with a weighted graph. It's also valid for white. I wonder if, well, that's probably because it's the biggest number that fits, maybe, which is a combination of all the colors, right? Because white is supposed to be the combination of all colors, right? At least in the, what do they call it? A positive, not positive, additive coloring system. Yeah, the additive coloring system means that you're adding all the colors. And if you add RGB to the max values, they generate white. That's why that is the value for white. And then black is all 0 because there's no light in that pixel, which means there's 0. So yes, some photography for you. Okay, so for the weighted version of that same graph, I also have it here. What you do is you put these things in parentheses, and then you put numbers to them. Okay, so this here is the same graph. It's not the exact same graph because I did make it directed, and as you, I mean, that would be kind of scary if I picked the same numbers, but the same arrows too. Well, that's kind of scary. Okay, all right, but I have an E at some point. Yeah, okay, that's okay. So anyways, so this is a graph. Here we have A going to B and C. We have B not going anywhere. We have C. Okay, so that's different than the one that I thought. So that would be weird if I thought the same graph from last semester. But okay, we have C going to B, we have D going to B, and then we have E just forever alone kind of thing. Okay, so when we're representing this with an adjacency list, what you do is you're no longer just listing out the vertex name. You are listing the vertex along with the weight associated with that connection. So you put that in parentheses typically, but that's not part of like the official designation. You just, you know, you can put a pair of number and identifier, or identifier and number. Okay, so what you do is, again, A is going to C and B, so you list C, and then you put the value of that weight. That means how long it takes to go from A to C, and then you put that in parentheses, and then you put the next one. So then A to B takes 1. So this is read as A to C takes 2, and then A to B takes 1. C to B takes 5, which we can see here, and then D to B takes 1. As you can see, when we're dealing with a directed graph, the number of these pairs that you have should be equivalent to the number of edges that you have. There's 4 lines here, so there's 4 of these here. Okay, let's do one more custom example. Oh, that's almost the same as before. Okay, that's different. So let's call these nodes 1, 2, 3, and 4. And then let's have these be weights of 8, -1, -3, and 1. Okay, just so you can see negative edges. So if we're doing the adjacency list of this, we would have 1, 2, 3, and 4. And what we're saying is that there is an edge going from 1 to 4 with a comma of 8. And then there is an edge from 2 to 1 with the value of -1. There's an edge from 3 to 2 with a value of -3. And there is nothing at 4. So there's also one from 3 to 4. So with a value of 1. Okay. Now, why did I choose to make this confusing? Well, just to show you that this is how you probably would look like in a computer for you. Well, except from starting from 1, you start from 0, right? You may have a pair that's 2 numbers. But just remember, the first number is the vertex name, and the second number is the weight, okay? So that's why I wanted to show you this. So don't get confused if you see 2 numbers and you're like, what the heck? Just be consistent. I'm not saying, I mean, heck, you could say the first value is a weight and the second one is the edge name. You could do that, but then be consistent about that, okay? So don't get the mix and match. I prefer the method of listing the vertex first and then the weight. So here I'm saying from vertex 1 to 4, it's a weight of 8. Which is equivalent to what is in the graph. From vertex 2 to vertex 1, there's a weight of -1. From vertex 3 to vertex 2, there is a weight of -3. And then from vertex 3 to vertex 4, there is a weight of 1. Okay? So that is how you would represent a weighted adjacency list. Okay? So that's it. So this will be where I would have finished But again, I'm going to do the next class stuff. But before I go on, any other questions? Also, isn't that a -1? Where? Did I screw up something? 2 to 1. No, I think I'm okay. 3 to 4, 1. Oh, maybe. Only if it... No, actually, no. It would be in 2's complement, I think. Right? Oh, man. 219 was summer. Brain is gone. But if you're thinking about unsigned integer, this would be the biggest possible number. Which RGB is also unsigned. So unsigned means there's no positive and negative in the range. It's just all numbers. So like 0 to 256. So I see what you're saying. Okay, this is where the fun begins, I suppose. All right, let me copy this other graph. Well, you see if you guys have any questions. Otherwise, you can take like a 1-minute break while I copy the next graphs for the next lecture. So these are found in so oh, that's not it. Okay, try that again. Oh, so it was 1 year ago that I did the machine learning lectures for Dr. Taba's class. Okay. The only reason that I'm actually copying this graph is because I have, well, hey, I have the answer, so I suppose I can check if I messed up. But more importantly, because I can fill up these. This right here. And then this. So, does anybody have a preference on which you'd like me to show you first? Breadth first or depth first? I would like to get rid of all the green. Breadth first. Okay, we'll go with breadth first. All right, close enough. And then let me copy and paste this twice. Will be one for each algorithm. So while I do this, let me kind of walk you through the basics of what we're going to be doing. And you said breadth first, so this will actually be a queue, not a stack. So we're going back to our beginnings of the class when we talked about queues and stacks, because these algorithms rely on those very basic data structures, but very useful data structures. So when it came to doing, so first of all, I hope I don't need to kind of tell you the motivation for doing traversals, right? I mean, we kind of talked about that motivation when we were talking about trees, right? Being able to kind of see how the graph is structured, especially because there's no nice and easy way of drawing a graph. Like, I mean, there's really cool programs. In fact, I offer extra credit. I think I have it somewhere listed there. Like, if you want to do a program that, given an adjacency matrix that you code, it will generate a graph where there's not that many crossings, then that'd be cool. But it's not as easy as you think. But essentially, traversals allow us to kind of get a feel for what a graph is like, okay? And to see the ordering or the distance that certain nodes are from other nodes and how the graph is connected. And so the two main traversals are going to be breadth first search and depth first search. And to have a direct comparison to what we covered with trees, breadth first search is actually the level order traversal. Remember, level order traversal in a tree is the one that's just kind of going by levels, right? So like at the root of the tree, and then the children of the root, and then the grandchildren, and so on, right? That's what we use for like a heap, right? We want to make everything nice until the last level where it's everything to the left, right? That's level order traversal. That's breadth first search traversals in general. That algorithm that you do that you're being able to kind of achieve that is actually done with breadth first search. In fact, what I'm about to show you now, this algorithm, could actually be directly applied to a tree to achieve the level order traversal. So like if you want to go back in that assignment where you did it and do the level order, you could use this queue system to do it. In fact, you might have done it. You might have Googled that at some point to figure it out and done it. Because I think I can't remember if I make it do the level order or not. Depth first search, on the other hand, is like the other traversals that we did, like pre, in, and post order. In fact, the difference between all of them, they're all technically depth first search, but the difference is in when you print and which branch you take. A traditional depth first search doesn't really care which branch you pick. It just cares, and you want to make sure that it prints when it first arrives to a node. So, and by that regards, the most traditional depth first search of the traversals that we learned would be the pre-order traversal, because that one went print first and then try to go as far left as possible and then as far right as possible. The depth first search traversal is a greedy traversal. It's a greedy algorithm in the sense that it tries to just go as deep as it can into this graph, and until it hits a wall, then it backs out. So before showing you the implementation of this, which it's very kind of systematic because it's how you would code it, and you don't really get to code it, so this is your own experience with that. I'm going to instead first show you the sort of how you do it by hand, and then we'll go to the code. We'll go to this implementation version. So for that, I'm actually going to just copy and paste this graph. Maybe here. Okay. I'll just shrink it. So this is going to be breadth first search, okay? And like I said, in case you came in late to the class, this class is going to go on a little longer than usual, probably half an hour at least. So depending on how fast we get these two algorithms done, really. Well, we have one more after this I would like to briefly go over, which is topological. But there won't be a class on Wednesday, so if you gotta go, that's fine, you can go, and then you can just watch the replay for the rest of the class later. I've also, by the way, I do see somebody claimed it already. I made a smaller claim for the extra credit that you should claim only if you think you're not gonna reach the 10,000 points, so that you can maximize your point usage. And then maybe the last day I'll do like a 50 points, so you can get those extra points, you know, those last bit points you might have accumulated, okay? So anyways, it's tiresome to do this stuff. If you're thinking breadth first search from like a visual perspective, what you end up doing is you, first of all, there can be a lot of breadth first search traversals for a graph. Unlike a tree, there's no root node, at least in a traditional point of view. You decide what the root node is, and it's kind of like your entry into the tree, which if you think of a linked list is kind of like your head pointer. So in this case, I could just very well say that like this is my root node. As similarly, I could say that this is my root node. Okay, so in this case, I am going to pick this as a root node and just go from there. Okay, so what I want to do when I'm doing a breadth first search traversal is I want to print as I visit. So my output is initially going to be the S, just because I'm already there. From there, I'm going to go to any of the nodes that are directly children of that node. So that is that one, and that one. So I'm going to add all the three of those to my output. However, doesn't matter which order you add them in, okay? It's irrelevant in that case. So I'm just gonna go from left to right. I'm gonna go A, C, G. My recommendation for you is just, if you really have this coded with pointers, just take them the way they come. Maybe you probably have a vector. If you were to implement this, you would have a vector of pointers, and each of those would hold, basically, each of those would be an edge pointing to that vertex that they belong. So you can just traverse in the way that they were added, and you're good to go. If you're trying to be fancy, you can do it alphabetical, but you know, again, if you actually have this implemented, it'll just be in some chaotic order. So, yeah. Anyways, from there, we can say we kind of finished the direct children of the starting node. The next thing we do is we want to get the next layer. So that's going to be the grandchildren. So the ones that are a distance of 2 away from that. So that would be this one here, this one here, this one here, this one here, and this one here. So it actually turns out it'll be pretty much everything else that is in here. Why? Because any of those nodes, you could go to the root, so the S, with 2 hops, right? You could do 1, 2. Oh, I lost that. You could do like 1, 2. You could do 1, 2. You can do 1, 2. This one actually you can go 2 ways, right? You can go this way or you can go this way. So that brings up another point. With the tree, you know, the big rule we said thou shalt not do is like connect. You know, no sort of inbreeding with that. So like you can't go and do this, right? No diamond problem with trees. With graphs, it's YOLO. They can be connected all the way you want. In fact, if it's like, you know, strongly connected graph with high degree, things are going to be all messed up around. In fact, those are what cycles are, right? If you reach a node from 2 ways, essentially it's a cycle. By the way, what I'm showing you is for an undirected graph, but the same thing can apply for directed graphs with slight modifications. So anyways, because all of those are connected to the root node by a hop of 2, you just add them into the next sort of set of these. I'm gonna just add them in the way that it kind of came out, which is that. But it doesn't matter. So if I was to ask you what the pre-ordered traversal for this graph is with a starting node of S, I would take that as an answer. But I would also take as an answer that. Or pretty much a combination of any of these. In fact, the fact that you can combine these 3 in many different ways means you're going to have 9 combinations there. And then you could have, wait, 9 combinations? No, I'm doing permutation versus computation. Go refresh your 251 or 351 math to find out the number of combinations you could do here. It's like it's like let's see, whatever the combinatronics thing for this. I forgot already. I'm tired. But yeah, it'll be a lot of different answers, which is why I would like to ask all of you to please do not make your TA's life hard. For the final exam, when I'm asking you to do one of these traversals, just go with the alphabetical ordering of this. So that would mean that the answer that I would really be looking for would be the S that has to be there, and the ACG, they have to be in this sort of set here. But the rest of these B, D, F, E, please try to maintain them in an alphabetical order. So that would be E, F, H, okay? 3 factorial. Is that what the combinatronics is for that? 3 factorial? Okay, that makes sense, yeah. So that would mean 3 factorial here times 1, 2, 3, 4, 5 factorial there. So that would be 3 times 5 factorial would be, 5 factorial is what? 120? So 5 times 4 is 20 times 3 is 60. Yeah, so 120 plus 3 factorial, which is 6. So that means we've got 720 different answers for this. Do you think your TA wants to figure out if your answer is one of those 720? He does not. However, it's not like he has to generate all the answers to figure out if yours is right. It's easy for him to check it. So, however, make his life easy. Do it alphabetical when you're doing the answer. We're not gonna think you're all cheated and came up with one solution. You know, I mean, don't do that though. That'd be bad. But I'm saying, just go with that so that the TA's life is made easier. Okay. So yes, anytime you got to decide which one to take, just pick alphabetically or numerically the ascending order. So yes, otherwise you're not going to lose points, but the TA will be very angry at you, and he's a student like you, so yeah, don't release your anger on him. So okay, so anyways, that is how you would do the breadth first search, sort of like on a test or something. You know, it's quite simple and trivial. However, if I was to tell you to code this, you might start to be like, oh, how do I do this kind of thing? You know, there's some trick to it. Which is, I mean, it's like when I show you, okay, this is level order traversal in a tree, and you're like, oh, okay, cool. I just kind of look at this, and then I tell you, oh, go code it, and you're like, oh, shoot. Well, if it's in an array, you're like, easy, just print out the array. But if it's with pointers, you're like, oh man, I gotta go around and hop around the whole tree to be able to jump between here and here, and then becomes a whole, something that seems easy becomes like a very, very hard, right? So this is where queues come to the rescue. Okay, so with a queue, a little Boolean array, and your graph, which can be represented with adjacency list or matrix. I'm not gonna show you matrix or list anymore. I'm just gonna show you the graph, but you can very much as well do the same thing when you're actually representing them like that. But with a combination of these three things, you can do a breadth first search / level order traversal. Okay, so what you're gonna do is, first of all, initialize your visitor array to false, which I'm going to represent with a blank, so I don't have to erase, and then a 1 with visited. Okay, so it's easier to show you than to kind of tell you, but the main idea here is this. First of all, you gotta pick a starting node, so we're gonna pick S, and what we're gonna do is we're gonna look at all the neighbors of S, so all the children per se, which are A, C, and G, right? So what we're gonna do is we are basically going to add them all to the queue. And then when we add them all to the queue, then we are going to say we're done. Okay. Actually, the first thing is when you visit a node, you want to print it out. So we will print out S to our output. So we'll have a little kind of output array or just C out, whatever. Okay. So add S to your output because it's always going to be the start node is going to be the first thing to print out. Just like your root node is always the first thing you print out in a pre-order traversal. Okay. So then add all of the children to the queue, and then you're done. And then from there, you start taking things out of the queue. And of course, the queue means that things that are added first come out first, right? First in, first out. So you will jack it out of the queue, and then you're going to look at the visited array. If something is visited, you will just discard it. But if it's not visited, then you're going to mark it as visited, and then you're going to work with it. What you're going to do with it is you're going to add all of the things that this one's connected to the queue. If you want to be efficient about this, don't add things that have already been visited. But if you do, then it's okay. It's not that big of a deal. And then once you go ahead and add all the things that are visited, then you can say you're done. And then you take out something else from the queue. You add all of the neighbors that have not been visited to the queue, and then you keep going. Okay. So if that didn't make sense, that's okay. Because like I said, it's so much easier if you see an actual example. It's not a hard algorithm if you just follow along. So we'll go ahead and do that. Okay. So as I said, the first thing you're going to do is add to your output. So we have the S because that is going to be our start. S for start, by the way, if you didn't pick up on that by now. So yeah, what we want to do is we want to make sure we mark the S as started. Maybe, you know what? I'm going to go ahead and move this array to this side of the screen so I don't block it with my head. Okay. So yes. Actually, we can probably zoom in to intensify the magnification quality of this. Okay. And again, this is a BFS algorithm, breadth first search. Okay, we have marked it as visited. In fact, maybe we should do a to-do list here. So mark as visited add children, which will say they're all the edges connected, which we can say adjacent nodes. In fact, that's probably a better terminology. It's more math-like. Add adjacent nodes that are not visited. And last thing, which is first, is add to output. DQ and add to output. So that's our to-do list, okay? All right, so let's go ahead and do it. So we are going to start out, I guess, it's, you know, the first thing you should do is just throw in your beginning node to the queue, okay? Done. All right, so I guess now we can start the loop. So DQ, so we DQ DS, we add it as visited, so we put a 1 there, and then we're gonna add all the adjacent nodes to the queue. Again, the order doesn't matter. I'm just gonna go be consistent and add them alphabetically, as you should in your exam. So A, C, and G, okay? Next, what I wanna do is I'm going to DQ the next thing. So I'm gonna go ahead and DQ, well, I always DQ the front, so you get the A out. So we got the A out. In fact, here, let's be visual about this. So we get the DQ, and then we add it to the output. But make sure you also mark it as visited, okay? So mark it as visited. And then, you know, we still got things in the queue, so maybe slide them forward. And you can implement your queue as a linked list to make it as fast as possible, but you can also do a circular queue with an array, and that'll be okay as well. So yeah, let's go ahead, and then since we're looking at A right now, we need to add all of the neighbors of A, so all the adjacent nodes. So those are both B and S. So we go ahead and add B, but S we don't add because it's already been marked as visited. So we do not add S to it, okay? All right, that's it, we're done. We're done with that node. So the next thing we want to do is we would like to take out C. Let's DQ the next thing. So we DQ it, add it to our output, mark the visited array as already been visited, and then add all the neighboring nodes to the queue. So C has a bunch of neighbors. It has D, it has E, it has F, and then it has S. But S we don't add because we already have it visited, right? So don't add that to it as well, okay? So we got D, E, F, and S. Yes, all right. Cool. All right, let us go ahead. And this is where things get a little interesting, because even though you want to keep it alphabetical, it's going to get not alphabetical. But that's okay, because you added it to the queue alphabetically, so that's what the TA is going to expect. Okay? So, plus they start to see a pattern. If everybody else selects the same thing, they're like, okay, this must have been the way the algorithm led it. So, did we add it to the, yeah, we added to the visited queue. Okay, I was making sure with the Boolean array was updated. All right, so take out the G now. Sorry that it keeps moving. I don't know if there's like I wish there was like a lock system to this. So mark the G as visited. And then go ahead. Here, let's slide this down so we don't run out of space. And add everything that the G is adjacent to the queue. So H is adjacent to it, and F is adjacent to it. So we'll be alphabetical about it. So we're going to add F. Then we're going to add H. We do not add S because it's been marked as visited. Now, this is interesting. You see up there, there's two Fs. Not to worry. It will solve itself. So it's okay if you see duplicates there, okay? They will always add duplicates if they're not marked as visited. So not to worry. Okay, so let us go ahead and continue this so that we can all go eat at some point. So, all right. We got the B next. So mark the B as visited, so don't forget to do that. And then add all adjacent things. So we got the A and then nothing else, but the A is already marked as visited, so hooray, we don't have to add anything else to our queue. Cool. All right, let's take out the D. D marked as visited, add everything that is adjacent to D. There's only one thing adjacent to D, and that's a C, and it's already marked as visited, as you can see here. So nothing happens there either. So cool. As you can see, the closer you get to the ending, the faster these go. All right, take out E, mark it as visited. E has a couple of neighbors. It has a C, and it has an H. So, and neither C has been marked as visited, so we don't add that. But the H has not been marked as visited, so we should add that. Okay, so yes, so E only has C and H. C is marked as visited, H is not. So we go there. Okay, cool. All right, now we're going to take out the first of the F's. F has not been marked as visited, so we mark it as visited. And then we're going to add all the things that F is connected to that are not marked as visited. So that C is already marked as visited. G is already marked as visited. And then it's not connected to anything else. So we don't add anything to the Q though. That's nice. All right, we take out another F. But here's the thing. This F that we took out, when we try to modify the visited array, we're like, oh, it's already marked as visited. Therefore, do not add it to your output. Throw it away. Like, shoo, it disappears into the void. Okay. So maybe I should flip my instructions to say the mark is visited before you add to output, because you do want to check if it's visited, and if it is, you don't want to add it to the output. Otherwise, you're going to get duplicates. Okay. So that's probably something. Yeah, I should have probably said that. Okay. All right. Take out the H. The H is not marked as visited, so we can go ahead and mark it. And then add everything else that is connected to it. So E and G, but they're both marked as visited, so nothing to add. Then we take out the other G, but this time it's already been marked as visited, so it also goes into the twilight zone. When your Q is empty, that is a sign that there is nothing else that you can visit. That doesn't mean that here's the thing. Your Boolean array may not have everything marked as visited, but it doesn't matter. At this point, you're done. Here's a question for all of you that are watching. When do you think will there be a scenario that something in the Boolean array will not be marked as visited when you have finished? What does that mean about that vertex that is not marked as visited? So what does it mean? What does it mean? No edge to it. It is not connected. I like the second one. I like that it is not connected a little bit more, because it kind of tells you more. So here's the thing. What I can tell you, the fancy way, is that there does not exist a path from your starting vertex to that vertex that is listed. So if we had a vertex here that we're going to call vertex X, okay, that is here, and it doesn't have marked anything to it. What that means is that vertex X has no path to S. So yes, it is, as you said, it's not connected. It might have its edges to other things, but it is part of another graph. Okay, so it's another component of this graph. So if what you're looking for, from a networking point of view, breadth first search allows you to see what is connected in your network. So like, this is me like sending out messages to everybody who's connected to see if they're there. And and if I don't get back something from X, that means that X is not part of the network. It's shut down, it's disconnected, or something. Now, here's the thing about this. This algorithm is cool and great, but it does have one requirement, and that is to have this visited Boolean array, right? You can't get around that though. What you can do is you can build it on the fly. So when you first see a vertex, so if you don't know, suppose that you are blind as to the graph. All you see is what's next to you. So you cannot see any grandchildren. All you can see are your neighbors. What you can do is, assuming that each of these vertex are uniquely identified by some value, they have a uniquely identifiable number, you can build this array as you go. So you can basically add things to this Boolean array and say, okay, I visited this node, I visited that node. So it's kind of like it's like you go on an adventure and you're meeting people and you keep track of their names. So that way, if you meet a person again, you know that you met them already. That'll only work if every person has a unique value. So like an IP, for example, that is unique. If you don't have a way of identifying things as unique, then you can't do the breadth first search, because you could end up going in circles and things like that. So, a bit of a headache. Does that make sense? Any questions about the algorithm or how it works before we move on to that first search? I'm glad that you guys thought about that, though. That means that you guys are following along, so that's good. I'm happy. So yeah, now that you know that, you could have done that for the assignment. I can't remember if I made you do level order, but if I did, then yeah, you could have done that. Maybe you knew that already. Who knows? Okay, so since I see no more questions, we shall move on to the next algorithm. The next algorithm is depth first search. So that's the other one. Okay. So again, you want to print when you arrive to a node. And again, it's greedy. So when you start, you pick one of the nodes arbitrarily. We're going to go ahead and pick C. From there, when you arrive to the node, you're going to keep going as deep as possible without going back. So you remember where you came from, but you keep going from there. So from there, say we go here. Actually, no, let's say we go to the D. From the D, though, you kind of reach a dead end. The only way is back. In which case, then you are allowed to go back. So you go back to the C, but you don't print it out, though. You only print out the first time that you arrive to a node. So you have to remember, again, all these algorithms, it's important to be able to have each vertex or each node have a uniquely identifiable number or something, okay? That's why like networks and stuff, like you have to have something unique, like IP addresses or MAC addresses or something. So from there, let's say that you go this way. Then you go here. And then from there, you wouldn't go here technically because you already been to the S. So you would go maybe here, and then here. But you already been there, so you would stop there. At which point, you would backtrack. You would backtrack here, backtrack, and then go here and here. Okay? So that first search kind of works like that. And it's the same thing as pre-order traversal. So if you want to do it using a systematic way, it's like almost identical to how breadth first search works, with the only difference being that instead of a queue, you use a stack. So we'll actually kind of speed along on this one. Okay, so we're gonna again we gotta pick a starting node. And you could build this array on the fly, but since we know that the contents of the graph, we're going to mark them all. And again, the first thing you want to do is, well, I guess in this, you pop from the stack, which pops the last, the last item inserted, LIFO versus FIFO. And then check, before you add it to the output, check if visited. If not, mark as visited, otherwise discard, or let's use the word continue. Discard. Okay? And then assuming that it is not visited and you're still there, then add it to output. And then add neighbors, or again adjacent vertices. So add adjacent vertices to stack. Again, so that we are all on the same page for the graders, just add them alphabetically or in increasing order, just numbers. Okay, so that's basically what we're doing. Pretty much the exact same thing as the other algorithm, except we're putting it in a stack instead of a queue. That's it. That's the only difference between these two algorithms. Okay, and if you could do the breadth first search very easily in code by just using recursion, because remember, recursion is stacks. So yeah. All right. So again, to start out the algorithm, so before you start out this loop or whatever you're doing coding it is add to the stack the starting node. That's just, and then your indication that you're done is when the stack is empty. Okay, that's your exit from the loop. Okay, so let us go ahead and pop that from the stack. So we go ahead and pop it. And then we add it to the output. So, oh, I forgot to have an output here. I'll put the output in the bottom this time. That way it doesn't like keep accidentally scrolling down. Oh, actually probably will when we do this. Yikes. Whatever. we will deal with it. So in this case, it's probably better to put it this way. I'll just put it really close to that, okay? And just make sure that we don't get confused with that. And that. We got 29 beers. I guess you guys have nothing else after this class. All right, but hey, Wednesday no class. Get home. You know, well, you're already home probably. Well, hopefully most of you are. If you're still on campus, and my condolences. Okay, because you get traffic at that time, so it sucks. Okay, so we mark S as visited, and we are going to add all the neighbors to the stack. So we're going to say A, and then this is where it gets a little interesting here, because we want to it's stacked, so we want to keep making what we're inserting at the top, right? So like that. You have a campus class. Oof, that sucks. You know, F in the chat, basically. Do we have an F here? Yeah, we do. Right here. F is for you. All right. So we got ACG, and again, because we're going alphabetical, they actually get inserted in that order, right? Because you know it keeps pushing it in. So A, C, and G. Okay. So now that we added them, then we can go ahead and move on. So we're gonna pop out the next thing from the stack, which is the G. Check if it's not visited. It's not. So we add it to the output and mark it as visited. And then we just add all the neighbors that are not visited into the stack. So that is S is already visited, so we don't want to mark that. But F is not, so F would go here, and then H is not, so H would go here. So that's the 3 spots, right? As you can see, I have to keep pushing things up, so that's why I'm like leaving space. So you know, scroll it up. Oh, the symbols are wrong, by the way. I'm using the top and bottom backwards. Top, bottom. I don't know why I like my stocks to have the top be on the bottom, but yeah, okay. So it doesn't matter how you do it on a test. Anyways, we can go ahead and pop up the next thing of the stack. That's the H. The H is too small. Okay, there we go. It's better now. Mark the H as visited. Then now we got still the H in there, and I'll add all the neighbors to it. So that is E and G. G is already visited, so we don't add it, but E is not. So we are going to add that to the top of the stack. And then, you know, what we can do is we can scroll it up and have extra space. Okay, so that's it. Yep, that's it. So just keep going. Got the E now. The E is not visited, so we mark it as visited and add it to our output. And then that is connected to C and H. H is already marked as visited, but C is not. So that is going to get added there. Okay? And just so you can see visually what this is doing, it's going S to G, G to H, H to E. Okay? That's where we're at right now. So then we're going to take out from the stack the C. C is not marked as visited, but now it is. And then add all the neighbors. So C's like the friend of everybody, I guess. It's neighbor to F, D, and E. So we're gonna go alphabetical again. So we're gonna add D. E is already visited, so we won't add it. F is not, so we will add it. So now we're looking at this. Okay. And then we move on. Add the F, mark it as visited. And then we got C and G. C and G are both marked as visited, so nothing to add there. That's nice. As you can, this is gonna start that part where like nothing's probably gonna get added at any point soon, because we only have left is A and B really. So D's gonna come out, but D is already visited. Oh wait, no, it's not visited. My bad. Not visited yet. Don't try to skip ahead. Okay. And then we would add a C, but it's already visited, so there's nothing else to add. Okay. Now we're going to take out the F. The F is already visited, so this one we are going to throw away. And visually what is happening right now is from the E we went to the C. Oh, we screwed up. We added an F when we shouldn't have. Failed. Undo. Okay. So, oh wait, no, we didn't screw up. That's just me screwing up. Oh, shoot. Okay. F. See, this is all Ilya's fault. Okay. So F. All right. So F is here, and then why is that F there? That is weird. That F should not be there. No, it should be there. That's okay, because what we did is we went to C and then to F. So that's going like that. Okay. We're good. It's all under control, guys. So the F, now we're at the F, but the F has a C and a G, which are both visited, so nothing happens. Okay. So we're okay. Everything's okay now. The D comes out. The D is up there, so that is not visited. So that's kind of like, we basically went, so what we did here, I'll do it in a different color, is we went from the E to the C to the F, and then we backtracked to the C, and now we're going to the D. So that's actually what's happening, okay? Ignore the weird arrow that just appeared. So, yes. Okay? So mark the D as visited, and then move on. So now we pop up this F, but the F is visited, so we throw it away. We pop up the C, which is visited, and we throw away, and that's the equivalent of us basically backtracking a little bit. From basically to D to C, and then the F there, and then finally back to the A that we see here. Okay, so that's pretty cool how that actually worked there. So A is marked as visited now, and then we add the neighbors of A, which are B and S. B is of course the only one that's not visited, so we add only B there, which then comes out of the stack. Mark that as visited, has only one neighbor, which is A, which has already been marked as visited, so you don't add it. Now the stack is empty, so you try to pop again, and then you segfault, right? No. You want to make sure you don't, you check before you try to pop that the stack is not empty. And when you do that check, and then you see that it's empty, then you say, I am done. And yet again, if there is a vertex that is not marked as visited, that's okay. That just means that it's not connected to this section of the graph. Just like with the breadth first search. That's it. That's all there's to it. 2 algorithms. If I made you code them in an assignment, which I don't because they're pretty trivial. Plus, you kind of want to have them in your assignment 11 because they help you to see if the thing is working. So, yes. Okay. Finally, the last thing of the day. We're actually not that, we're only half an hour past, so that's okay. So, I guess my 45-minute computation was not too off. But last algorithm that I like to show you, this is like the bonus one. Topological Sort. It's Topological Sort. Now, the name is misleading because it's not a sorting algorithm. It's just sort of another type of traversal. And I suppose I should add it to the output here, so because otherwise people will be confused if they're searching for the lectures. So maybe I'll put Topological Sort here. Topological Sort. My dog is like, yo, it's time to eat. Okay. So I have a graph here that I'm just going to copy over for this to speed up again. Okay, so what topological sort is, and I have a more fancy way of doing topological sort if you watched last semester's. I'm not going to show you that. What I'm just going to show you is how it works, and then if you were to code it, then you'd have to kind of get a little creative with it. It's not that bad, but if you want to see how you would actually code topological sort, you can watch last semester's video or just go on the internet. What topological sort is, first of all, it's only for directed graphs, because you can see with the breadth first and depth first search, we're assuming that it's undirected, but it works also with directed graphs. You just basically add the edges that are actually coming out of that matrix, or sorry, that vertex, right? Topological sort is a strictly directed graph traversal per se. Okay, the way it works is that you want to print out all of the vertices that have no incoming edges to them. So they're in degree. So you have to talk about what the in degree and out degree is. So I have a definition here for that. I don't. Okay, I'll just write it here. So in degree and out degree. What in degree stands for is the number of edges coming into a vertex. And then out degree is basically the same thing, but coming out of vertex, okay? So out degree is the number of edges coming out. I guess off a vertex is more grammatically correct. But yeah, so basically when you say the in degree of a vertex, you're talking about how many edges are going into it, which is very hard to figure out if you don't have you don't have pointers in both directions, by the way. This is like a terrible thing when you're coding. But out degree is easy. You just look at your like vector of like pointers that are coming out of that, and you just count it, and you're like, I'm done. Okay. So, however, topological sort is all about the in degree, not the out degree. So that's why it can be it's like 50,000 times easier to code if you're working with an adjacency matrix. In fact, pretty much every single algorithm is easier to code when you're working with an adjacency matrix, actually. But you can do it with both, technically. So anyways, what you're going to do with this is you want to print out all of the nodes that have no in degree first. And when you print them out, you remove them from the graph. And then you start looking again for nodes that are now having an in degree of 0. And you can only remove nodes from this graph and add them to your output if and only if they have an in degree of 0. So because I'm going to be doing this a couple of times, let me just go ahead and copy and paste this. First, I'm just going to show you how you would do it, and then we'll actually add it to the output. So right now, we have a couple of nodes that have an in degree of 0, and those are 2 of them, A and G. C does not have an in degree of 0 because it's got an arrow coming in from A. B has 2 arrows, so that's even worse. D has 1 arrow, F has an arrow. E has like 3 arrows coming in. S has 2 arrows, F has 1 arrow, and N has 1 arrow. So the only ones that have no arrows are these. So what I'm going to do is I would add them to my output, and then all of the arrows coming out of it, so all the out degrees, I would remove from the graph. Well, actually, let's pick one of them. Say we pick the A, so you remove the A's ones, okay? From there, after we've removed A's arrows, so we would mark it to the output. So we said something like A is in our output now. Now you pick again from the vertex that you have available, a vertex of in degree of 0. So actually, while you could pick G, you could also at this point pick C. The other ones still have something coming into them. So now you have a choice between C and G. So just like the other traversals, there can be more than one answer to this. Again, let's just pick alphabetical. So we're going to go with C. Okay, so we're going to add C to our output. So how we will do that is, hold on, there we go. We will add C there, and then we're going to remove all of the edges coming out of C. So that one, and that one. Okay, so now we have 3 options. We actually have B, we have G still, and then we have D. But since we're going alphabetical, we're going to go with B. So we add B to our output, and then we remove any out edges from it, which are that. Here, we didn't release anything new, so we're still just having just 2 things left, which are G and D. So we're going to go with D. Okay, so we're going to add D to our output, and then take out E, and take out F. So now we got 3 nodes, E, F, G. So let us go with F. Actually, oh, no. E is not okay because E's got an input from G. So that one's not okay. We only have G and F actually. So let's do F then because it's alphabetical. So we can go ahead and erase that. And then now we have G and T available. So where G is lower, so let's go with G now. So we got a G there, and then get rid of that. So now we got E and T. Let's go with E because it's slower alphabetically. And that removes that. And then we only have one choice now, which is T. So let's just take that one then. And then we can get rid of that. And then we have S. And then get rid of that. And then, of course, we have N. And then we are done, right? But as you can see, if we pick one of the other 2 letters, like if we didn't go alphabetical, we could have a different answer, right? So that's topological sort. And it's useful to kind of, well, it has a lot of uses, but it can tell you like redundancies of things, you know, based on like how many inputs you have to certain things. It can also be very, very useful to figure out if there's a cycle. Because suppose you have the following network. Okay, at the beginning you're like, okay, I can remove this one. But now you're like, well, I can't remove this one because I have an input. Cannot do that one, cannot do that one. So at this point, I'm like, I can't remove any of these. So if there is a set of vertices that when you do topological sort, you cannot remove and you can't add to the output, it means that them together form a cycle, which cycle detection is very useful. It can be good for avoiding when you're trying to make something more efficient, or if you're trying to remove like a short circuit. There's so many different things you can do with it. But cycle detection is like a critical thing. In fact, minimum spanning trees, one of the algorithms about it, which is one with the videos that you can watch, will have to deal with cycle detection. So this will be one of the ways that you could do that. So how you actually would do this in code, again, I said I wasn't going to talk about it, so I'm really going to go light on this. Is if we go back to the I think this is the same example from the beginning of the class. So if we have the following right there. So we got A to B to C and then D, okay? If we graph that, it graphs like this. A goes to both B and C, B doesn't go to anything, C goes to B, and then D goes to C, okay? So what you can do if you're trying to do topological sort, like actual implementation of the algorithm, is you delete the lines vertically and horizontally. One or the other, actually. So like, for example, this is what you start out with, right? So to figure out which of these you can remove, you look at the vertical lines. So if a vertical is empty, first of all, ignore the diagonals, okay? So like the diagonals, just get rid of them. I know you would have 1, 1, 1, 1, just ignore diagonals, okay? Otherwise this thing breaks. Once you remove the diagonals and you only leave the edges that exist, and these could be weighted or unweighted, no problem. I'm just saying the rest of these are infinity, -1, whatever you want to code them as. Look at the verticals of it. So look at these verticals. The ones that you can remove from this, from the topological sort, are the ones where the vertical are empty. There's nothing on the verticals. If you see, both B and C have two things coming into that because they have two vertical lines. That is the in degree right there. If you want to find out the in degree of a graph using an adjacency matrix, just measure the vertical. If you want to find out the out degree of a graph using an adjacency matrix, you can measure the horizontals. As you can see, B and C both have an in degree of 2, A and D have an in degree of 0. However, looking horizontally, you can see that B has an out degree of 0, and then C has an out degree of 1, D has an out degree of 1, and A has an out degree of 2. As you can see, B does not have anything going out of it. So out degree horizontal, in degree vertical. Very useful thing to know. Just not used in this class at all, but useful to know in general, okay? But for topological sort, I suppose it's used. So what you do then is you can just go ahead and remove those. So like, let's say you remove, let's say we start out with A. Okay, so we're gonna pick A to remove. Actually, no, let's pick D to remove. So if you're gonna remove D, what you do is, well, first of all, you see that there has an degree of 0, which it does because the vertical line is empty. So what you do is you erase the horizontal line. So you go in here and you just erase the horizontal line like that, okay? So that means that this 1 becomes a 0, okay? When you do that, you look at the vertical lines again and look, see the next, and well, add it to your output. So add D to your output. Then look at the vertical lines again and see what you have available. Well, this is already done, D, so you can check mark it or whatever. Keep a visited Boolean array, kind of like the other algorithms. And then you see that B still has stuff in the vertical and C has stuff in the verticals. So your only choice is A. So we're going to go with A. So what do? Erase A's horizontal one. That will be the equivalent of removing the out degrees of A, which are in degrees for other things. When you do that, add it to your output, and then mark it as done. So now look at the vertical lines again. We have B and C left. B still has something in the vertical, so we can't touch that. C doesn't, on the other hand. So we can go ahead and say, okay, we're going to work with C. So with C, add it to your output, and then go ahead and remove the horizontals from C, which is this one, and then go on. So now, all that's mark it as done. B is the only one left. B has nothing on the verticals. Perfect. Mark it as done. Add it to your output. Technically, we'll erase from here, but there's nothing to erase. And then you'll be done. So as you can see, topological sort is kind of not that bad to implement when you just have an adjacency matrix. Doing the same thing with just pointers, like not lists, just pointers, is a nightmare, which I do not wish on my enemies. Okay, so yes, that is topological sort in a very quick manner. Most of these algorithms you're going to go over again in the analysis of algorithms. So pretty much all the graph ones you will. So that's why I'm not too concerned about not going in detail. But it's nice to know. Topological sort is a nice algorithm. It's cool. So that's it. We have finished everything that I wanted to. So all that remains of the semester is minimum spanning trees and Dijkstra's. Dijkstra's we're going to go over on Monday after the holidays, after Thanksgiving. And then Wednesday, maybe we'll do a little bit of algorithm analysis, like for like 20 minutes or something, talk about some algorithm stuff, and then we'll do a review. So from this row, of course, remains minimum spanning trees. For that, I will link you to two lectures that I have from last semester, where I'll make you watch the first one and then a piece of the second one. The reason is because there's two minimum spanning trees algorithms to cover, and you only need to choose one to do for the assignment. So if you want to see just the first video and you're happy with that, you can choose that method. You can also choose the other method that involves disjoint sets. I welcome you both to watch both videos and learn both methods, but you only really need to know one for the exam and for the assignment. So, yes. All right. So I'm glad that you guys stuck around for the extra long lecture, but now we have Wednesday off. So it'll be great. Any questions about the material that we covered today? We still have 27 viewers, I think, too. All right, so I see nothing from anybody. So in that case, we're done. CSBO due Sunday. I guess, yeah. It's been available for the full semester. Is it when it's due? Let's see. It's due December 3rd. Actually, no, that's the last. That's assignment 11. Yeah, it is due. It is due on Sunday, so you have a week left to do it, basically. Well, 6 days. So yes, so get going on that. I think the reason why I did that is because then 11, you have like more time, because I'm assuming you're gonna watch the videos for it at some point over the weekend or on Monday before this. I mean, for the Dijkstra class, by the way, you don't need to know the minimum spanning tree. So if you don't want to watch those immediately, you don't. But I welcome you to watch them, especially since it's a long weekend. So that's why I made them do the other way around, because it gives you more time. Instead of having like minimum spanning tree be doing like this weekend or something, and that'd be bad. So, okay. Well then, I presume that you guys will have questions on Discord or an email on Canvas over the next few days if CSBO is due Sunday. So I shall look forward to those. That's like really, really fun assignment. If you watch some of the lectures from last semester, there's some videos on that as well, like demos of it, so you can see. But thanks for staying, guys. I wish you a safe and fun Thanksgiving. Eat some good food, I guess, if you guys are doing stuff, celebrating. And I'll see you guys next Monday, all right? Take care, and good luck with the assignments, since the next time I'll see you, it'll be a thing of the past, right? So, all right. Thank you all. Happy holidays indeed. Happy Thanksgiving, and well, I don't know what Kwanzaa is, so I don't mess up things up, but happy holidays for all of the holidays that are happening. So, bye.